My name is Yi Yang. I come from Intel ODL team. I work on ODL SFC project and OS/NSH support. My topic is fix Openflow Multi-writer issues in OpenStack integration environment by using Flow programmer. In this talk, I will introduce what Openflow Multi-writer issues are and what VxLAN issue is. Then I will introduce Openflow plugin, Flow programmer. After that, I will illustrate Openflow pipeline in this integration and introduce what changes we did for this integration. Then I will show demo. What are Openflow multi-writer issues? Because we need to integrate multiple Opendaylight applications in one system. Okay, so multiple applications will operate Openflow tables on one OS bridge. So you will encounter table conflict, flow conflict, pipeline conflict, and write operation, synchronization, etc. So why before we didn't realize this? Because every application just runs alone. But when we integrate network and SFC, we encountered these issues. So how can we fix these issues? I proposed the Openflow plugin Flow programmer last year. I implemented this and submitted to Opendaylight. Actually, we also have VxLAN issue in OpenStack integration environment because we need to create tenant VM and service VM in one compute node. Currently, these two VMs cannot communicate by VxLAN GPE. Why? Because VxLAN GPE or VxLAN is implemented in OS kernel module. So VxLAN implementation limited this. So how can we fix this issue? We introduced the Ethernet plus NSH encapsulation for SFC. We implemented VxLAN GPE and NSH in OS. We published this patch to this GitHub. Now, ODL Boron release has already supported this OS version, and only one choice for NSH officially. Here is the Openflow plugin Flow programmer. I implemented it inside our Openflow plugin. It's an Openflow plugin feature. Each project can call this Flow programmer APIs to program Openflow. Here are Flow programmer APIs. If the application will fix the multi-writer issues, it should call these APIs. The first API is a register application. That means register this application to flow programmer. The first parameter is application name. The second parameter is maximum table ID of this application. Then the application can get its table offset. For example, if your application is the first registered application, its table offset is 0. If your application is the secondly registered application, its table offset is the firstly registered application's maximum table ID plus 1. If your application is the thirdly registered application, its table offset is the firstly registered application's maximum table ID plus the secondly registered application's maximum table ID plus 1. So.
Are you saying this is an existing API or this is one you created?
This API is provided this flow programmer.
Okay.
Every application can call write flow and remote flow to operate its own tables. These two APIs just for each application's own tables. These two applications just for table 0. Every application can call these two APIs and flows to table 0. So here, every application must carefully to call these APIs. This is a pipeline before, without a flow programmer. Here you can see SFC has this pipeline. NetVirt has this pipeline. Here you can see table 0. SFC uses table 0. NetVirt also uses table 0. Here SFC has table 10. NetVirt also has table 10. But they have different purpose. Here it's a transport address table. Here is a director table. So it's a table conflict. Another issue is we need to combine these two pipelines into one pipeline for NetVirt and SFC integration. Here we use the flow programmer API, so we can combine these two pipelines into one pipeline. Here you can see actually this gray pipeline is the SFC pipeline. It's a first registered application. This light black box, this is a NetVirt pipeline. Here you can see table ID is changed. Okay, it's automatically allocated by a flow programmer. So when the package enters table 0, table 0 flows will classify it to this branch or this branch. For SFC package, it will go to this branch. If this package is for local VMs, table 10 will resubmit this packet to table 0. So SFC classifier can get it and steer this packet to local VMs. If it's just for NetVirt, table 0 flows will classify it to this branch. Okay.
Like you mean if the bucket, the coming bucket didn't match the SFC pipeline, you will send it back to the classifier to send it to NetVirt pipeline?
Yeah, no.
Here, like, it could be like an endless loop.
No, not a loop. For example, if the package from tenant VM, right? It should be go into classifier flows, right? Classifier flows will push NSH header, right? So it will be match SFC pipeline, match the SFC pipeline. Okay.
Which is why in table 10 you send it back to table 0 if it didn't match.
Because table 10 will pop NSH header. It knows this packet should be going to local VM, so it will pop NSH header, then resubmit table 0. Here, table 0 has some flows to match it and send it to local VMs. Okay.
NetVirt pipeline?
No. Send it to VMs, not pipeline. Just table 0
Okay.
has output action.
So why didn't push it for the first time? Why we need to go through all this and this?
Yeah, for non-SFC traffic, it doesn't go into this, just go into this. Okay. So the gray pipeline just for SFC traffic, the gray pipeline just for non-SFC traffic. Okay. We did a lot of changes in Opendaylight and OS. In OS, we implemented VxLAN GPE and NSH. We also implemented two kinds of encapsulation. One is VxLAN GPE plus NSH, another is Ethernet plus NSH. We have published this patch into GitHub, so anybody can get it and use it. We also changed the Openflow plugin to support this OS. We ended push NSH actions and pop NSH actions and some new match fields. So this change is very big. So that is the base for SFC network GPP. We also changed the SFC network GPP to support this OS. Here we changed the SFC classifier and Openflow runner to support two kinds of encapsulation. These changes are not upstreamed. It's only for my integration demo. Here is my demo topology. You can see we have two compute nodes. We run OpenStack controller in this node. This is just compute node. We start SF1 in this node, SF2 in this node. We start web client in this, web server in this. And here is Opendaylight. For general traffic, it's not SFC traffic. The package will go through this path. But for SFC traffic, it will go through this path. Here are package processing procedures. Here at the beginning, it's a general Ethernet packet. When web client sends this packet to BRINT bridge, classifier will push this header, Ethernet plus NSH header. So SF1 will get this package, then send back to BRINT bridge. Okay, SFC Openflow renderer flows will steer this packet to VxLAN GP port. VxLAN GP will encapsulate this packet with the VxLAN GP header. So here we get this packet. Then this packet will go into this VxLAN GP port. This VxLAN GP port will decapsulate this packet. So SF2 will get this packet. Okay, VxLAN GP header is removed. Then SF2 will send back the package to OS bridge BRINT. SFC Openflow renderer flows will pop Ethernet plus NSH header. So finally, web server will get the original Ethernet package. Okay, that's the whole processing. Next is demo. Because I cannot access my lab machine, so I just show recorded demo, recorded video. Here you can see we are starting DevStack install OpenStack. It's a OpenStack controller node. What? So slow. Here you can see it's a DevStack install log. It's the last message. Here you can see BREX bridge, BRINT bridge. Right? It's for controller node. Here we log in OpenStack. So slow. What? Here we need to add flavor network, tenant network, service network, and WinF images. create subnet net. Here is the end images. Here you can see VNC link. Here's that SF. Here you can see SF1. We can see login this. It's a VM1. Here you can see VM temp port. This is VM2. This is the service function one. Here we run REST Python script to create service function check. Here is the service function 2. Here we change REST script. Here you can see we log in VM and SF. So slow. Oh. Here you can see Openflow rules. It's generated by ODL SFC. Why so slow? Here we start this Python script to emulate the service function. So when we run this Python script in SF1 and SF2, SF1 and SF2 will act as firewall or DPI. Here you can see we pin VM2 from VM1. It's okay. Here we start a web server in VM2. We can duplicate VM2 from VM1 because it's in VM, so it's slow. Here, Openflow rules were not generated, so pin just use network rules, not SFC rules. Here we add SFC rules. Here you can see SFC table. So here you can see SFC service function change under the service path are created successfully. Then let me see here. Here it's a service function usually working. You can see service function handle NSH packet. Right? Here pin is okay, but it goes through service function chain, not network pipeline. Okay. That's my demo. Any question? No question.
That could be an option to the solution that today is working in OpenFV, because I mean, in OpenFV there is another solution for coexistence of NetVirt and SFC.
Yeah, I know. Currently, the new network cannot support this service function chain. In all the OpenFV integration, it just used workaround to fix the VxLAN issue. Just workaround, not real
The VxLAN,
fix.
yes. The
Yeah.
VxLAN issue, yes. But the table zero coexistence, it was also fixed, right? The table zero conflict.
Yeah, we use Openflow plugin flow programmer to fix multi-writer issue. We also use Ethernet plus NSH encapsulation to fix the VxLAN issue. So actually, we fix two kinds of issues. Okay. So, thank you.